Hey everyone, welcome back. Let's talk about another medium problem on Leetcode today. Word break Leetcode 139. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given a string s and a dictionary of strings wordDict, which is given as a list, and we should return true if s can be segmented into a space-separated sequence of one or more dictionary words. Note that the same word in the dictionary may be reused multiple times in the segmentation. Then in example 1, the given string Leetcode can be segmented into two words Leet and code using the dictionary words Leet and code. Hence, we will return true as our answer. Similarly, in example 2, the string apple, pen, apple can be segmented into the words apple, pen, and apple using the dictionary words apple and pen, where the word apple is used twice. And as we can successfully segment the given string, we will return true as our answer. And finally, in example 3, for the given string cats and dog and following dictionary words, the string s cannot be fully segmented. For example, we can try segmenting the string as cat, send, and then the remaining string og cannot be segmented. Or if we try to segment the string using the dictionary words cats and then again the remaining string og cannot be segmented. Hence, we will return false in this case. We have already tackled part 2 of the problem, where the goal was to construct all possible sentences by adding spaces in the given string using the word dictionary. But here the problem is simpler, where the goal is to determine whether the given string can be segmented or not. And in terms of solution, one of the naive approach can be that we generate all possible substrings of a given string using two nested loops. And for each substring, we check if it exists in a dictionary. And for that, we can add these dictionary words to a set for the O1 time lookups. And if a substring matches, for example, if the substring is apple, then it will have a match. Then, in that case, we will recursively check the remaining part of the string, which is pen apple, and repeat the same process. However, in this way, we will be generating a lot of unnecessary substrings. For instance, substring like apple or plip, which may never be useful if it is not a match in the dictionary. So instead of generating unnecessary substrings, a more efficient approach is to start with the prefixes in the given string, say with index I at the beginning of the string, and check if it matches with any word in the dictionary, or we can use a loop on the dictionary and check if the given string begins with any of these words. And if the string starts with a valid prefix, for example, apple here, then we will recursively check if the remaining part of the string can be segmented using the dictionary. And in the end, if we reach the end of the string, that means we were able to successfully segment the string, and hence we will return true. Otherwise, we will return false. Now let's quickly see this in action. So we start the DFS at index 0 and try to form the prefixes up to the length of the string. So we will form the prefixes like A, AP, APP, and so on, which don't exist in the word dictionary, until we form the prefix like apple, which exists in the word dictionary. And note that since word dictionary is given to us as a list to perform the fast O1 lookups, we would convert this dictionary to a set before performing any lookups. And continuing further, we will create more prefixes like apple P, apple PE, and so on, but none of the prefixes exist in the word set. So we continue with the path where we identified the valid prefix apple and move to index 5. And again, starting from here, we attempt to construct all possible prefixes of increasing length like P, PE, PEN, and so on. And since the prefix pen exists in the word set, we continue along this path and move the iterator I to index 8, and again try to construct all possible prefixes like A, AP, and so on. And eventually we construct the prefix apple, which exists in the word set. So we continue along this path and move the iterator forward. And now we are at the end of the string. So that means we were able to successfully segment the string, and hence we will return true in this case. But if we couldn't find any recursive path where we can achieve full segmentation, in that case we will return false. Now the time complexity of this approach is O of 2 to the power of n, where n is the length of the input string. Because in the worst case, each character of the string is checked for all possible splits, which leads to n-1 potential cut points between the characters. And then the algorithm decides whether to make a word break there or not, leading to a binary choice at each point. Hence, the overall time complexity will be O of 2 to the power of n. And if you'd like a deeper understanding of why the time complexity is exponential, try drawing the recursion tree for a string like AAAA and wordDict with all the prefixes of the string. And you will see each character leading to multiple recursive calls, resulting in exponentially growing tree structure. And the space complexity will be O of n, mainly coming from the depth of the recursion stack, because in the worst case scenario, every single character is a valid word, forcing many single character steps. Now, from this example, it might not be immediately obvious that we have overlapping subproblems. However, once we know whether the string can or cannot be broken down at a particular index, that result will always hold true or false, respectively, regardless of which path we take during the recursion. For instance, consider the case where given string s is cats and dog and word dictionary has words cat, cats and sand and dog. And suppose we are trying to break the string into words, and if we break it at cat followed by sand or as cats followed by and, the remaining part of the string, which is dog, is shared by both the paths, and dog exists in the word dictionary, so can be successfully segmented. But we should not need to recompute its result for both paths. Instead, we reuse the result which is true in this case, which saves us from the redundant calculations. Similarly, here for example, if we know in any recursive path that starting from index 6, if the string cannot be segmented, that result will be false regardless of which path we take during the recursion. And once these results are computed, we should be able to reuse them instead of doing the redundant calculations. And this is where memoization or caching can help us, where we will create a cache or memo table to store the result for the substrings that we have computed. And once the result for the specific substring is known, which is either true or false, we save it in the memory, and later if we encounter the same substring, we can simply reuse the cached result instead of recomputing it. And now the time complexity reduces to O of n square, because for each index, we are checking prefixes of varying length up to n, which results in a time complexity of O of n per index, and hence O of n square for n indices. So the overall time complexity is O of n square. And the space complexity remains O of n for using the memoization array to store the result for each index, and depth of the recursion stack, which in the worst case can go up till n levels deep. Hence the overall space complexity is O of n. And now let's discuss the bottom-up dynamic programming approach to solving this problem. Unlike the top-down approach, where we use recursion, which results in the recursive overhead, and memoization, in the bottom-up approach, we iteratively build the solutions for smaller substrings first and use them to solve for the entire string. And this approach is centered around creating a DP table, where each entry DP of I represents whether the substring from the start of the string to that specific length can be segmented into the valid dictionary words. If yes, DP of I will be true, otherwise it will be false. So we start with DP of 0, which represents empty string, and DP of 0 will always be true because an empty string can always be segmented. Then we move the iterator I forward, and now I is equal to 1. So we will examine the substring of length 1, which is A, and since A does not exist in word dictionary, it cannot be segmented. Hence, DP of 1 will be false. And same will be the case for I equal to 2, 3 and 4, where the substrings AP, APP, APPL have no match in the word dictionary. Hence, the entry in the DP table for these lengths will stay false. And again we move the I pointer forward. And now I is equal to 5, and one of the substring will be apple, which can be segmented. Since the word apple is indeed in the dictionary, so DP of 5 will be true. Now for I equal to 6 and 7, it's clear that substrings apple P and apple p cannot be segmented. So dp of 6 and 7 stay false. Now the iterator I moves to 8, and this time we will get the substring apple pen of length 8, which can be segmented into the words apple and pen, as these words are in the dictionary. While this can be seen visually, how can we solve this programmatically? And this is where another pointer j comes in. This pointer moves from 0 to I to check if the string has segment at any point, which is the point where dp of j is equal to true. And in this example, those points are empty string and the substring apple, which have already been segmented successfully. And if we find such segment, then we just need to check if the remaining substring, for example here pen, can be segmented. That is, it exists in the word dictionary. So if both the conditions are satisfied, then the entire substring of length I can be segmented, and hence dp of I will be true. And this is the difference from the top-down approach, where we were recursively moving forward to solve the problem for the larger subproblems. In contrast, here we solve smaller subproblems first and build up to the larger problem. So coming back to our example, we start j pointer at index 0 and check if the substring from 0 to j, that is substring of length 0, can be segmented or not. And here the answer is yes, because dp of 0 is true. So then we will check if the remaining substring from j to I, that is apple pen, can be segmented. And the answer here is no, because apple pen does not exist in the word dictionary. So we move j pointer forward. Now j is equal to 1. And again dp of 1 is false because the substring a cannot be segmented. And this is how we will continue until j is equal to 5, where we see dp of 5 is true because the substring apple can be segmented. So we will check if the remaining suffix, which is pen, can be segmented or not. And the answer is yes, because the substring pen exists in the dictionary. Hence we will set dp of 8 to true. And again we move the I pointer forward and come to I equal to 9, where the string of length 9, which is apple pen A, cannot be segmented, and same will be the case for I equal to 10, 11 and 12. So the dp values of these lengths will stay false, and eventually we come to I equal to 13, where we see the string of length 13, which is apple pen apple. So again we reset the j pointer to the start of the string and iterate from a substring of length 0 up to I and check if the empty string can be segmented. And the answer is yes, because dp of 0 is true. So we then check if the remaining suffix, that is apple pen apple, exists in the word dictionary, and the answer is no. So we move the j pointer forward, and this time we check if the string of length 1, which is a, can be segmented, and the answer is no, because dp of 1 is false, and so on until we come to j equal to 5, where we see the prefix apple, which can be segmented. So then we check if the remaining suffix, which is pineapple, can be segmented. And the answer is no, because it does not exist in the word dictionary. So we move the j pointer forward and come to I equal to 6. And since dp of 6 is false, we know that the prefix string apple p cannot be segmented. So we move the j pointer forward. Now j becomes 7, and same is the case for j equal to 7. So we move the j pointer forward. Now j becomes 8, where we see that dp of 8 is true. So we know that the prefix string of length 8, which is apple pen, can be segmented. Then we check if the remaining substring, which is apple, can be segmented, and this time the answer is true because the suffix apple exists in the word dictionary. So that means the whole substring of length 13 can be segmented. So dp of 13 will be true. And now since the whole string of length 13 can be segmented, we will return true as our answer. Now the time complexity stays O of n square because of the two nested loops, where the outer loop checks whether each prefix of length n can be segmented, and the inner loop checks for the n substrings. Hence the overall time complexity is O of n square, and the space complexity will be O of n because we are creating this dp array of size n plus 1. Here is a quick code walkthrough of the algorithm we just talked about. with Java code on left and Python on right. First, let's convert word dictionary to a hash set for faster O1 lookups. Now let's get the length of the input string, let it be n, and create a boolean dp array of size n plus 1, where dpi indicates whether the substring of length I can be segmented into words from the dictionary. Now let's initialize the base case, which is dp of 0 should be true because an empty string can always be segmented. Now we run the nested loops, where in the outer loop we iterate over all substrings of length I from 1 to n, and the inner loop j runs from 0 to I minus 1, where point j represents a split point to divide the string from 0 to I into prefix 0 to j and suffix j to I. Now at each partition point, we check whether dp of j is true, that is the prefix of length j has already been confirmed as segmentable. If that is the case, then we check if the remaining suffix from j to I exists in the dictionary, that is if the suffix is a valid word. If both the conditions are true, then the current string of length I can be segmented. So we set dp of I equal to true and break out of the inner loop because we don't need to find other ways to segment the string once we know that at least one way exists. And after both the loops complete, we return the final result for dp of n, which indicates whether the entire string of length n can be segmented. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.